This is a joint work between my students, Erman and Huseyin, and another professor at UT Dallas, Zhiqiang. So I guess, thanks to a very good introduction of the first talk, it's clear that the cloud computing is becoming an important driver in many IT spending. And I think for all of us in this audience, I think the most important statistics is that almost nowadays 60% of the companies start utilizing cloud. And this is not a buzzword or something that's passing away. I think it's getting more and more attention. And one important thing is, of course, the security is one big problem. At least the companies who are worried moving to cloud mention security as a challenge. And of course, one of the tools that, as we have seen, is to use at least the security connection between the cloud and the clients, and the virtual machines and the clients. And of course, as the previous talk very nicely explained, that in order to get good utilization, cloud providers basically couple multiple virtual machines in one physical box and try to use VMMs to do logical isolation. And of course, this creates lots of potential issues, and I will skip 2 slides basically, thanks to the previous talk, showing that this may be attacked, and the attack could be potentially devastating to many different crypto keys. And there are many defenses, again, you see one before, that try to change the VMs and try to prevent such key attacks. So what we wanted to do is we wanted to fundamentally change how this could be done. Of course, crypto has many ideas that deal with this kind of issues. But of course, we were kind of thinking that the side channels may not be the only attacks against those kind of crypto keys. The recent software bugs like Heartbleed show that you can even disclose the key directly without any side channel at all. So this all creates the issue of how we can protect the keys. So in this work, we wanted to see the application of a very common idea from crypto, which is the threshold cryptography or secret sharing-based cryptography. And the main idea of those who are not as, or at least who doesn't remember the crypto class well, basically you have a secret key, it could be RSA secret key, and you share this key between multiple parties. So therefore, no VM or no party has the entire key, and they need to collaborate to do decryption or to do digital signing, okay? So you can assign these keys to different VMs. And furthermore, when you do the secret sharing-based framework, without changing your public key, you can keep resharing the keys. So this way, even if the attack is successful sometimes, any side channel or bug attack successful sometimes on some machines, as long as the attacker is not successful on all the machines all the time, you should be still okay, as long as you can do it. I will explain more on this resharing a little bit later. I'm going to skip the crypto part that much. It's very standard crypto. But basically, I want to let you know, I mean, the thing to just remember to understand the rest is, in order to do a decryption, let's say, assume you have L shares of the private RSA key, and any K of the VMs can come together and do the decryption. But during this decryption process, none of these parties send keys around. They just decrypt the message by using their shares. So this is quite standard, and it's been implemented a lot. So basically, what this change in a typical SSL part is, or session establishment, the VM, basically we call it combiner VM, interact with other VMs who has the share of the keys. And they send this partial messages to other VMs. And other VMs decrypt and partially decrypt them by using their share of the secret key. And it's sent back to the combiner VM. And combiner VM basically combines the results, and which will be the original signature or the original decryption. So we need to do this change in the, for example, the 2 parts that we have shown. So what does this mean? So in our setup, our assumption is that the defender or the owner of the VMs can do this secret shares Why? I will explain in a second. So basically, each VM will get some shares. Why they get more shares is that their connection between them is also through SSL, and those connections are also secret shared. So they are basically, so none of them has the entire private key of any private keys. So they do this secret sharing. So what this means is that then they establish a secure connection among themselves using their share of the secrets. So from client point, nothing changed. Client just know one application server, connects to that server, and starts establishing SSL session. And then, of course, this message and whatever that needs to be signed or encrypted needs to be sent to the other share of the VMs. And then those sign or decrypt is basically using their share of the private key and send it back to this combiner. And the combiner establishes session. They can use AES or other keys after this point. So of course, the interesting part or moving target type of defense of this kind of solution is that you can repeat this process as often as possible. So in our experiments, we can reshare the keys every 5 seconds without impacting the more. So basically, this defender, this could be also on the cloud, can do this resharing every 5 seconds or so. So the attacker, as long as cannot capture all the keys in less than 5 seconds, after 5 seconds, all bets are off. Basically, you restart the process. They need to be successful, get all the keys again. And of course, important part here is that from a client or outside connection, only the one that runs the application needs outside connection. All the other VMs that has the keys on them or shares of the keys can be behind some kind of firewall and only needs to connect with other VMs. So all the connections coming or going out of those VMs can be limited to other VMs. Therefore, they don't need to be accessed from outside, other than, of course, sharing. So, of course, this is a well-known idea from crypto. Now the question is what was the overhead of this idea? So we ran some kind of micro benchmarks and then two applications, typical web server and mail server application. We ran this on real Amazon environment. We got one large EC2 step and 9 small ones. And we use Apache HTTP benchmarking tool and some JMeter for the mail server. And on our site, on our campus, we have some kind of server that can simulate multiple clients at the same time. And all of this implementation done as a shared library in OpenSSL, so we didn't change the OpenSSL, and we don't need to change the application as well because it's doing in a transparent manner. And of course, one other thing is that you don't need any collaboration from the cloud to do this. So you can go and implement this for your own application server. So we don't require any collaboration from the cloud. So what happens is that this micro benchmark does is it just establishes a connection and closes it immediately. So for example, in one client, total takes 12 milliseconds. So if you do it regularly, it could be 2 to 6 times slower. So normally, just establishing connection, typically it may take 3 milliseconds. So similar high overheads just for establishing connection could be observed in other scenarios where we align 1 to 10,000. And here on the axis, what we are doing is that we have more and more shares. So we have total 10 VMs, and this shows that if you require 10 shares to be combined, of course, which means that each 10 share combination requires sending at least 10 messages around, and each machine does some operation and send messages back. So it can create some kind of network bottleneck. And in addition, it can also create some kind of computational overhead. But this is just for when we are establishing the connection. We have many more experiments in the paper, and I just want to show one scenario where if we use more VM, it actually could be used as a load balancing for the secret shared part. So for example, if you look at the case where we have 1,000 clients, and we have 10 VMs, but we need only 2 shares to be able to do the decryption or signature with RSA. As we increase the number of VMs we have, we can see, for example, in this scenario, we can reduce the total time. And the reason is that now the application server can choose any one of the VMs that has a share of the secret and can send a message to that VM. And therefore, this could reduce the congestion on any given VM compared to the case where we have only 2 of them and they try to do the secret sharing. So this is, as I mentioned, just for the crypto part where we use the public key infrastructure. But so the overheads can seem a little bit high, or high in some, according to a reviewer. But the thing is that if you couple this with some kind of application where there is some kind of computation is happening in addition to that, this is 1 here means like you don't do any secret sharing, and 10 means that you have 10 VMs and you have 10 shares need to be combined, which is quite a heavy load. And the overheads from application point of view becomes less and less. And the reason is that, remember, once you establish the channel using the public key, maybe you do some other operations, so the total overhead of the application from the client point of view would be very little, a couple of percentage points. And again, we have other examples with HTTP servers, HTTP clients, etc., which I don't show, but similar trends could be seen there as well. Of course, it should be clear by now that in our system, the total number of shares or total number of VMs that you put shares on, which is L, number of shares needed to be potential successful RSA decryption, which is K, and the resharing. Remember, in order to protect against successful side channel attacks or other attacks, we keep resharing the shares. Therefore, any capture share will not be meaningful after a certain time period. In our experiments, it's like 5 seconds, basically. So after 5 seconds, all the shares are refreshed. So now the question is, of course, we need to optimize for these parameters, and we need to figure out what are the nice values for that. So of course, we have 3 metrics here going on. We have the security option. So we want to reduce the probability of successful capture. We want to reduce, of course, we want to worry about the cost, because more VMs you have, more time consuming it is, etc. And we have, of course, the performance issue. As you see, there is some overheads involved. So we looked at the literature for successful attacks. Usually most of the papers publish the mean time to succeed based on their experiments, but we don't have the exact distribution of this, how the successful attacks work. So when you have independent, since our case, at every 5 seconds we start an independent event, we thought that, and look at the literature in statistics, exponential distribution may be a good thing. And then that's what we used as our thing. So this means that if your mean time to succeed for attack is, let's say, delta, then this would be the distribution we assumed of probability. So in other words, what is the success probability if the resharing period is theta? So if your attack has, on average, requires, let's say, 6 minutes to succeed, and if you do basically resharing of keys every 5 seconds, what is the probability that during that 5 seconds the attacker may capture the key? So that's the probability we used. Of course, in our case, the attacker may need to capture K keys at every 5 seconds. Remember, after the 5 seconds, we change it again. So we assumed in these probabilities that all the attacker doesn't spend any time to collocate its attacking VMs. So this is only about capturing enough number of keys in a given period, and this becomes a simple binomial distribution. And of course, costs we look at very simple. It's a linear function of the number of VMs you used. The other thing is also the understanding the L and K and its relationship to the overhead. So we don't exactly know that, but what we have done is, as I will come back to this slide again, what we have done is we fit our data based on our experiments to the parameters L and K, okay, to see how the different L and K impact the performance based on our result. And this is what we come from a linear regression. So using this performance metric, we plug it into this multi-objective optimization. So what we are trying to do is we try to minimize the success probability of an attack by choosing L and K. But while we are doing this, we want to make sure that we don't pay too much, and we want to make sure that the performance is not too much impacted. So given these, and given these values, what we can do is that we can search for the optimal parameters for under different scenarios. And what we done is that we wanted to keep the overhead somewhere between 50 to 200 milliseconds, let's say, per the key establishment period. And this is basically assume you have 2 to 16 different additional VMs. So basically, you can think these values as we look at the prices at the time of the paper writing for Amazon and multiply by the numbers. So this means like 2 VMs per year, and the last one, I'm sorry. The last one, 14. So this means like 2 additional VM per year, or 2 VMs per year, and this is 16. And then we assume that the attacker has basically succeeds in on average 10 minutes when they run the attack. So under these, for example, our calculations, the best would be that minimizes the attack probability will be 2/2. But of course, if you have more options, for example, you can see that you can do with 16/10 option. So you have 16 VMs running and you need 10 keys. Okay. And of course, now the probability of successful capture, assuming that mean time to a successful attack is 10 minutes. Of course, if the attack is, let's say, successful attack is 1 hour, take 1 hour for attacker to do it meantime, then of course you can see different parameters. The other thing is we look at how performance changes, and we fixed the cost largest in this case. So we gave the optimizer to play with 16 VMs. And we see non-trivial results. For example, if you limit the performance for 50 milliseconds, 16/6 could be the best choice possible, and so on. And sometimes, for example, in this scenario, the optimizer finds that we don't need to use even all of the VMs. 15 could be better. But again, this is using our performance based on our own data. So this kind of shows that I think there is more need to be done to see right parameters under right settings. To summarize, we think that secret sharing based schemes can be used without the cloud providers' help to protect against side channel attacks, and more probably, because as we mentioned, the client can only need to connect to the application server, so the other key holding servers may not need an outside connection. Therefore, they could be slightly more protected and so on. And the performance overhead can be very low for CPU-bound applications. So this doesn't mean that it's free for all the scenarios. Clearly, you need to pay more for additional VMs. But we kind of think that you may maybe reuse VMs for different keys and different sharing. And as we've shown that the optimal parameters can be found using a multi-objective optimization framework. So thanks for your time. If you have any questions, I would be happy to answer.
Let's thank the speaker. Please state your name and affiliation and ask questions, please.
Jethro Beekman, UC Berkeley.
Hi.
I was wondering, what is the performance of your OpenSSL implementation compared to a regular OpenSSL implementation?
As I mentioned, if we just do the SSL, so the client establishes SSL connection, and then let's say dies automatically. So, for example, in our scenario, it may take 12 milliseconds. In the normal case, that operation in total may take 2 milliseconds, just that part. But if you do it as a part of a bigger application, that overhead becomes much smaller. So in the initial part, we pay, of course, much more, maybe 4 times slower.
Right, but have you also tried it with like 1,000 clients at the same time?
Yeah, we tried. So I showed, I passed a little bit quickly. We have tried 1,000 clients and so on. Thanks. 1, 10, 100,000, etc. Sure.
Then I'll ask one question. So I mean, it's a really cool idea, but have you thought about any sort of, how would you sort of protect this key sharing process? Because now that could be another sort of attack surface.
Correct. So basically, this key sharing process, what we are trying to say is that the SSL connection used to share the keys are also using secret sharing. And the second thing is that we are kind of thinking that since these servers that holds the secret keys, their purpose is to just communicate with the combiner VM that combines the secrets, and so on. So they could basically have only limited network connectivity to limited basically IP addresses. So this can make it harder to attack them as well. Thanks.
All right, let's thank the speaker again.